Good day all, and welcome to this Lightbend webinar for December 7th, 2017, Advanced Akka for Architects. My name is Oliver White, Chief Storyteller, MC, and Newsletter Guy at Lightbend, and joining us today is my teammate Hugh McKee, Developer Advocate at Lightbend. So while I take a moment to introduce today's session and allow any latecomers out there to get settled, I'd like to ask our audience a quick poll question. And as an incentive to share your experiences, we'll be randomly selecting a poll respondent and mailing you a Lightbend t-shirt. So for those of you who don't know much about Hugh, it's fair to say that he's an Akka fan. After spending many years at Hewlett-Packard working with the actor model in Akka, he joined the Lightbend team in 2015. The main reason? To contribute to the OSS toolkit he loves on an everyday basis, as well as author some excellent educational materials and O'Reilly ebooks while he's at it. So when it comes to Akka, Hugh has got the sort of background that makes him a great presenter, since he actually lived the days of single-threaded, synchronous, and barely scalable applications in the real world and built a new sort of reactive system with Akka and other Lightbend technologies already. So he's going to join us today to continue to build upon those real-world examples from his past experience as an Akka developer, showing us how to take advantage of new OSS and commercial features, such as Akka Multi-Data Center Clustering for improving reliability across multiple data centers, availability zones, and regions, as well as Akka Cluster Sharding in a multi-data center environment, and how to use Akka Multi-Data Center Persistence for increased fault tolerance. Today's webinar is only made possible by the hundreds of happy Lightbend subscribers out there, in particular our fast-growing client Credit Karma, the financial services company that democratizes credit reporting for over 70 million users. They're looking for an engineering manager as well as a Scala engineer in their San Francisco office. You can find out more about this position and other open positions with our customers and Lightbend on our website under the Company tab. As always, this webinar is being recorded and will be shared with you next week. If you have any questions for Hugh, feel free to add them to the GoToWebinar control panel, and we'll see if we can get around to them in the Q&A part of today's session. As you know, if you're an existing subscriber, then you can always reach out for unlimited access to our expert engineering teams through the customer portal and ask all of your technical questions, what-ifs, how-tos, and best practices. So that's all I have to say for now. Let's hand it over to Hugh. Welcome, sir. Thanks for joining us.
Thanks, Oliver, and thank you everyone for attending. As Oliver mentioned, in this session, we're going to be covering some of the new features that the Akka team has been busily working on this year. It's kind of a present for us for the end of the year here, that revolves around this new capability of multi-data center clustering. And just as a quick kind of high-level agenda, we'll be covering some of the basics of the multi-data center clustering capabilities, how this works, give you hopefully a bit of intuition of how it works. And then we'll take a look at how things like cluster singletons and cluster sharding and persistence, and there'll be the two forms of persistence, the existing Akka persistence and then something new that the Akka team has been working on as well. So to start though, just as a quick kind of setting the baseline here, many of you know with Akka runs in the JVM, and what we do is we start up an actor system, and then within that actor system running in a JVM, we create actors, and then those actors start chatting away with each other. They start sending each other asynchronous messages. And this is just this diagram. I'm going to be using kind of this diagram a fair amount in this presentation. This diagram represents little red dots represent actors in an actor system. So this is a very common usage pattern for people that use Akka, where they run Akka in a single node, and maybe you're using Akka with Akka streams in a single node, or perhaps you're using Akka for doing some nice multi-threaded, highly concurrent operations. Actors are really good at that. Akka actors are really good at handling of that. But we're here to talk about clustering, and with Akka clustering, there's this kind of expansion of our universe in that we have an actor system that we can span across multiple instances, multiple JVMs. And so in this example diagram, what I'm showing here is, say, is an Akka cluster where there's 6 nodes running in the cluster. And the cool thing with this is that the actors that are running in all these different nodes in these different JVMs can talk to each other. They can exchange asynchronous messages with each other just as easily within a single node as across multiple nodes. You know, so the Akka is handling all this. So we just, as developers and architects, we implement our actors running in an actor system that's running in this, say, this distributed environment running in an Akka cluster, but we don't get involved with writing code for doing the messaging, the serialization objects and things like that. There's very minimal things that we have to do as developers to implement this, and Akka is kind of doing the heavy lifting here to make all this happen. So beneath the API, beneath the abstraction layer, there's quite a bit actually that Akka is doing for it here. And one of the things I wanted to just kind of review very quickly is that in a cluster like this, we have, say, multiple nodes running in the cluster. And what's going on kind of behind the scenes is that all these nodes are, there's an awareness at the node level of what the topology of the cluster is. So in this example here, there's 6 nodes, and each node is chatting away with the other nodes, keeping an eye on it. It's somewhat analogous to like you and I are in this kind of group chat. We're using our phones to chat with each other, and I've used this analogy before, where we send each other messages, and those messages are, you know, when you send a text message, it's a form of an asynchronous message. Now, really, the analogy I'm trying to use here is that, say we're in this boring group conversation where each one of us is sitting there and we're just firing off messages to the other 5 individuals in the group. And what we're trying to do is we send a message, like I send a message to you, you send a response back. So I say, are you there? And you send a message back, yep, I'm fine, I'm here. And we're just doing this. As I said, it's a boring conversation, but we're just constantly doing this. And what will happen is that, say there's a problem, or say there's some kind of network partition all of a sudden appears that cuts off a few of the members of this little group conversation. So say I'm on the right-hand side with somebody else, and you're on the left-hand side. And now all of a sudden, when you fire off a message to me saying, hey, are you there? You don't hear back from me. When you fire off a message to the other guy, the other individual that's participating in this, that's on my side of the partition, you don't hear back from that one either. So you hear back from other participants that are on your side of this network partition. So the result is that each one of us in a relatively short period of time can assess that, oh, there's this partition that's occurred, and I can see this other individual that's on my side of the partition. You can see the other 3 individuals that are on your side of the partition, but we can't see each other. So we're split off. So this is kind of a classic split brains type of a situation. And what happens is that both sides, we kind of split the cluster in half, and both sides declare these members, these nodes, unreachable. So this is kind of just a quick review of some of the mechanics that goes on within an Akka cluster right now. Now, start to split things out in a more broadly distributed environment. If we, a lot of people have been asking for this for a while, where we want some nodes in the Akka cluster to be, say, in one data center, and other nodes to be in another data center. Things get kind of interesting here. So I had a little fun, and I grabbed a world map, and then I kind of did a little bit of math and a little bit of calculation here, nothing elaborate. But what I wanted to show was these littler circles here. That are kind of, there's one centered over San Francisco, there's one centered over New York, Paris, Moscow, Sao Paulo, India, Japan, and so on. That circle has a radius of about 10 milliseconds at the speed of light. So what this says is that, in general, the best we can do sending a message, say, from San Francisco to Chicago, which happens to be on the edge of the circle on the left, getting just the message from San Francisco to Chicago is about 10 milliseconds. So the round trip is at least 20 milliseconds. That's a long time for us. I mean, we're developers, right? We implement systems that run really, really fast and really small periods of time. 20 milliseconds is a long time for us. And it's much longer than, say, the messaging that occurs between systems that are very close to each other on the network, say within a data center, where the message latencies is on the order of a millisecond, or maybe fractions of a millisecond. The other consideration here is that if we're trying to hook machines together and have them communicate together across a much broader geographic region, there's more likelihood that things are going to go, burp in the night with the networks themselves. Things are going to break more often in a more broadly geographically distributed type of network situation versus, say, within a data center. Not to say that data centers are perfect, and the networking in a data center can drive you nuts as well. And I've had this in my past life at HP. So theoretically, it has been possible for Akka to have a cluster that is stretched out, that is distributed across broader. In fact, one of the systems that I worked on with Akka, we did actually have a cluster that spanned between a data center in Austin, Texas, and a data center in Houston, Texas. And those two cities are relatively close to a millisecond apart speed of light, so it's not too bad. And it worked out reasonably well, but we did have situations where, and they were kind of driving us a little crazy, where we had these intermittent outages with the network. So that's what I'm trying to show here in this diagram, is that when we kind of stretch the nodes apart between data centers, you're kind of stressing Akka itself, because Akka is tuned to do all the monitoring and health checking of all the nodes within a cluster, low latencies, and the expectation that the network responds relatively quickly, and it's really there to detect breakages. So this is the big change with multi-data center. With multi-data center, what you do is you configure, in your configuration, you're configuring individual data centers. So in this example here, we actually formally do configure Akka, where there's 3 nodes in one data center and there's 3 nodes in this. And this is used by Akka to change the behavior of the monitoring that occurs within a data center versus that occurs between data centers. So that's what I'm trying to show with the different colors of the lines here, is in that the level of monitoring that occurs between data centers is fundamentally different than the level of monitoring that occurs within a data center. So within a data center, things are like what we know. If you've done any level of Akka clustering, everything that happens within a data center is the same. What's different communication between data centers, the monitoring that goes on between data centers is looser. It's not quite as tightly bound. In a way, there's tight coupling between the nodes within a data center and looser coupling between those. In setting up the configuration for multiple data centers, there's a few changes that have been added to the Akka configuration. And what I'm showing here is an example of that. There's this setting where an individual node is identifying itself as being one of the nodes in, say, data center A. And then also there's another configuration setting where we show that the multiple data centers here are data center A, B, and C. So that's shown here in this diagram, where we've got, say, these 3 data centers that are set up. So again, we've got these individual clusters that are running within a data center, and they behave very much like, they behave actually exactly like what we're used to with Akka clustering. But the ability exists here where actors, say, on data center A can send messages to actors in data center B or a data center C. The big difference, though, is that there's that change in the way the monitoring occurs between these different data centers versus within data centers. So I kind of like to think of this as clusters within clusters. We have data centers that have their own individual clusters that are unique to that data center, but then each of these clusters within the cluster can communicate, the actors in those clusters can communicate with other actors across all these data centers. Again, so the big difference here is that, say, for example, we have a network partition that occurs between data centers A and C and B. So B is cut off, and data center A and C are cut off from B. So here, what happens is that each of the data centers is aware of the fact of what members in the data centers they can see. So A can see all three members in C. C can see all three members in A, but neither A or C can see any of the members in B. B can see itself, but it can't see A and C. So they're all up, but they're cut off. But that's the only reaction that happens with Akka. Contrast that, though, with this scenario, where, say, a node goes down in data center B. Now, again, A and C, what they know is that that node is unreachable. But B reacts differently. This causes a state change in the cluster state of B. B maybe that has split brain implemented. So it reacts by recovering from a split brain type of a situation. Or it recovers by, say, we're running in Kubernetes and the node comes back up in a few minutes, or shortly after it fails, because it's one thing that Kubernetes does is if a process goes down, it restarts it. Say there's a momentary outage where this particular node is gone. B is reacting to that on its own. A and C are aware of it, but they're not really doing anything other than being aware of the fact that this member's down. So there's some additions that have been made for cluster events. And as a quick review, cluster events are where actors can register themselves with Akka to say, hey, send me messages when these type of events occur. So there's still all the events that occur within the data center, but now there's new events that occur across data centers. So this is an addition that has been added to the cluster events, where you can receive notification of, say, like that scenario, B had a node go down. Actors that have registered for cluster events in A and C could be notified that this has happened, and you could use that in whatever way you want for doing some form of cluster aware actors. So what's interesting though here is that what's happening, you define these data centers in the configuration, but the data centers themselves don't have to actually be physical data centers. It's just kind of the way you configure it. So you have the option, say, within a single data center to kind of group these clusters within clusters, where you have these individual small clusters running in a larger cluster, or clusters running in a supercluster. And this opens up something that people have been doing. Some people have been doing this, or some people have been asking about this, is that say that each of these so-called data centers is a logical grouping of nodes that represent, say, a particular function. So what I'm showing here is that, say, there's 3 microservices here that are running and configured to run in different data centers. This gives each of these data centers some level of autonomy from each other. You still have the capability for actors to communicate with each other across between the data centers, but there are inherent differences in that these are kind of semi-independent clusters that are running within the so-called configured data centers. So again, you don't have to physically separate them. It's up to you, but you do have that option now because of the looser monitoring that goes on, where you can have data centers that are farther apart on the network and over maybe more precarious network connections. Kind of like me in London in a hotel room trying to do a webinar. So this has an impact on things like cluster singletons. And this probably isn't going to be a surprise based on what I've been saying so far, in that there's really no change to cluster singletons. You have cluster singletons, but it's not a cluster singleton for all data centers. It's a cluster singleton per data center. So this hopefully will hammer home the point that we kind of have these individual clusters running within a data center, but they have a level of independence from each other. So in this diagram, I'm showing 3 data centers. Each of these data centers independently can have its own cluster singleton. They have no relationship with each other. Building on that, because with cluster sharding is built on top of cluster singletons. There's a shard coordinator per cluster sharding implementation. That's a cluster singleton. And then there's shard regions, so there's a shard region per node. And this is kind of the higher level mechanics of cluster sharding, in that it's autonomous. They're independent per data center. So there's implementations of cluster sharding that are unique and independent of each other in each individual data center. Here's another example. Here's a little bit different, where we're starting to get into something that's data center aware, where we've got, say, cluster sharding implemented and set up to run on data center C. And then on A and B, we've created shard region proxies. And those shard region proxies are configured to, when they receive a message that is destined for the cluster sharding environment running on C, that they'll simply forward those messages to data center C. And this is done with a fairly simple, straightforward change to the API for setting up a proxy. So I've got a little bit of example code that I pulled from the documentation that shows that we created this proxy that is going to send all of this messages. It's going to forward all of its messages on to nodes that are defined to run in data center C. And as you might expect with Akka persistence, it's the same thing, because Akka persistence is built on top of cluster sharding. Cluster sharding is built on top of cluster singletons. So you can implement Akka persistence, and it would be, again, it's independent per data center. There's a unique instance of Akka persistence in each data center. So you have the choice. You could say one of your data centers is using Akka persistence and other data centers are not. The choice is per data center. So per data center is kind of like a subcluster and a supercluster, a cluster within a cluster. So moving on, though, that's kind of the cluster sharding, cluster singletons, Akka persistence. Everything's pretty much the same. It's just running within a data center, but there is a multi-data center persistence add-on that has been created by the Akka team that spans data centers. So it's kind of interesting. It's Akka persistence, functionally Akka persistence, but it's got this ability to replicate between data centers. So basically, you're ending up with replications of everything that's happening in one data center happens in the other data center. So here's an example where, say, events have come in to be persisted for an entity in data center A, and then those events are replicated over to data center B, and then they're persisted, and the actors on both sides of the wire here, in both data centers, there's an actor for each entity in data center A and data center B, however the multi-data center Akka persistence is set up. And it's bidirectional. It could be that events are being persisted, say, in B. So the third event here is persisted in data center B, and it's replicated back over to A, whereas the first two were first persisted in data center A, and they were replicated over to B. But this presents some things that need to be considered, where there's always the possibility that you could have events coming in on both sides, and say in this two data center example, which will result in the ordering of the seeing of the events in each data center will be different. So in this scenario that I'm showing here, the order of events is different in data center A than data center B. You have to take this into consideration if you were to use multi-data center persistence, in that this would not break, say, the consistency of your data. You would have to take this into consideration. So one example is that there's the context-free replicated data types, the CRDTs. Those are ideal for something like this because the order of changes does not matter for CRDTs. It could be that there's a commutative type of operation. You know, say for example, I'm using a simple example here, but say it's a bank account. In a bank account, you know, you have deposits and withdrawals. If it's in some cases, this is a simple example, but say it doesn't matter what the order is, the bank balance ends up being the same no matter what the order of events is, because it's kind of a commutative operation. I know this is kind of a naive example because there could be situations when you overdraft, things like that, that you don't want to have happen, say, where data center A ends up in an overdraft, whereas data center B does not. But hopefully you get the point here that you have to take these things into consideration. So it may not be a fit for all the different scenarios, but if it is, the goal here is that you can have persistence where there's a lot of plumbing built in to give you this replication capability between data centers. So as a result, to do this, there's actually a new class. It's called a replicated entity. In Akka persistence, there's a persistence actor class that you extend. Here, it's a replicated entity actor class. So here's a Scala example, and there's some key methods that have to be implemented for these things. There's an initial state method that creates, an empty state object for the entity, but the more interesting ones are the command handler and the event handler. So the command handler handles incoming commands, the event handler handles events. So commands are requests to do something, events are statements of fact, something that has happened. So there's methods that are implemented for both. Here's a Java example of the same thing, where we have a replicated entity in Java. And also note in the definition of this class that you do declare the command and event and the state classes or interfaces. So those things are known, to the implementation. That they're all formal part of the way you set things up with replicated entities. So here's a sample of what happens in a command handler and what happens in an event handler. The thing I wanted to kind of point out is where do we actually persist the event? So you can see in the command handler, the command comes in, and typically the scenario is the command is validated. If the command is valid to be performed on, then it results in the creation of an event that's persisted in an event log. So that's what's happening in the command handler here. You can also see that there's an end then method, and this is used to do some nothing really like stateful. It's not used to say do a critical operation, because what's happening is the persist event is a transaction that happens in a database. And right now, multi-data center persistence is built on top of Cassandra. Later on, hopefully they'll be adding more databases. Right now it's Cassandra. But in any case, the event is persisted to a database. That's a transaction. That transaction happens, and then after that transaction is completed, the method is called. So it could be that the event is persisted, but the end then never happens because we had a failure in between the successful completion, completion of the persistence transaction and before the end then could be called. So in this case, if we had a failure at just the wrong moment, the event is persisted, and before we can send a message back to the sender, say the ad was posted, we go down. So that's not going to happen because it's happening in a non-transactional type of situation. The event handler is invoked once the event is persisted. And there's some other interesting things that I'll show you in a moment, but mainly the event handler is there to change the state of the event object itself. Say in the bank balance, it's the one that actually does the change of the balance of the account. So this is what's kind of interesting, though. We have, say, a 3 data center environment where we're doing the replication between 3 data centers. The command comes into data center A, that doesn't persist, but then the event handlers are invoked for an actor that represents that entity in all 3 data centers. So that's what I'm trying to show in this diagram, is that first the command handler comes in, and then second the events are processed in each of the data centers. So this is the mechanism that's used to keep these replicated instances of the entities in sync with each other across multiple data centers. So there's quite a bit that's happening underneath again in Akka to do this, or Cassandra. So there's actually 2 options for the actual physical replication of the events. One is using Cassandra as multi-data center replication. The other one is to use Akka for replication. This is fully described in the documentation. We don't have time to go into details, but it's kind of another nice or good to know. I mean, you have to make a design decision when you implement this, but from a coding standpoint, I think it's really important to know what's happening mechanically in some of these different instances of the entity actors that are running in the system. So there are scenarios that are discussed in the documentation, and here's another example. Say we have a conflict where we have different changes that are occurring to the same entity at the same time across multiple data centers, and one of the scenarios is the last writer wins. So the last change is the one that wins. And in this case, the last change could be based on a timestamp. So there is this capability that's provided here with the replicated entity where you can have the event handler is processing the incoming events, and it looks at the timestamp of its state and compares that timestamp to the state of the incoming event. If the event is newer than the current state, then it accepts the event. If it's not, it ignores that event. Something like this. So it's kind of the last wins kind of an implementation. Here's a Java version of that same thing. So the documentation has Scala versions and Java versions already in it. One more thing, just to show there's other things as well that this class provides, this replicated entity class provides, but there's an event trigger. This is a method that's called after the event handler is called. And the documentation is going to do a much better job than I can about what actually happens in here. But the idea is that if you want to do some additional work after the event has been processed and propagated between data centers, this example goes into kind of a multi-step process where once all the data centers have processed the event, then it can trigger some kind of a state change in the entities. So just wanted to kind of show you there's other methods that allow you to kind of hook into the flow of the processing of commands and events in this class. Here's the Java implementation of the same event trigger. So I know we went through it really quickly, and I apologize for the audio issues at the beginning, but in summary, we've got this new capability where we can have individual clusters that are set up and function just the way we know. Nothing's really changed there. And the new thing here is that we can have these individual multiple clusters now talk to each other, actor to actor, sending asynchronous messages. And the new configuration here is more tolerant of outages. It doesn't react the same way that outages react within a cluster when you have outages that react between data centers. So it opens up these new capabilities, like having individual clusters be an implementation of a specific microservice, and gives you the possibility of using actor communication to exchange messages versus, say, using HTTP REST as a kind of the only form, or maybe doing asynchronous messaging with Kafka. There's this other channel that you can use to communicate between these data centers. So the documentation is available. I've created some bit.ly links for them. There's already in the Akka documentation, there's a really good section on multi-data center clusters. And then there's another document that's available for the commercial add-on for multi-data center processing. This is, again, it's still, I don't think it's completely final yet. I think it's very close, but there's definitely some really good documentation there. So if you're interested, you can check out both of these pieces of material and get way more information than I provided in this session. So with that, I think I'll turn it back over to you, Oliver.
All right, Hugh, thanks so much, and thanks for bearing with us on the audio trouble. I know it's no fun to have to interrupt in the middle of it. Before we get to some questions about which there are many about Kubernetes, believe it or not, I wanted to run through just a couple resources that our audience can run through and get a better handle on what's going on. There's a lot of questions coming in about how do you program actors, for example, and whereas this is not the right forum to ask questions about programming actors in Java or Scala, there's a wonderful presentation that Hugh did for us earlier this year in September called Akka Revealed. And this is a rather more introductory look at Akka, starting from the actor level and going all the way up to the clusters and data centers level that Hugh just did a deep dive on. So when we share this presentation with you, there'll be hyperlinks for this. There's another wonderful resource, Hugh, if you could go to the next one. Now, this is Hugh's very own book. This actually goes a bit deeper into the actor model itself and why is Akka such a clear choice for so many large enterprises in this era of distributed computing. So I definitely recommend you check out Hugh's O'Reilly book if you haven't seen it already. It's a wonderful introduction to the actor model and why it makes sense in today's world. And finally, next slide, please, Hugh. For the advanced members of our audience out there that are looking to start harnessing the power of some of these new features right now, give us a chat. Give us a chat. Give us contact us. We can do a brief 20-minute chat with a Lightbend representative to let you know how we support our clients in not only the design and build phase, but also the production phase when running, as well as learn a bit more about our enterprise suite, which has some of these commercial features that we were discussing before. So that's all I have to say. Let's go to a couple questions here. Hugh, since recently you were just speaking about the event handler, one of our audience members asks if the event handler is represented by an actor or whether it's something else.
That's a really good question, and it is represented by an actor. So in Akka persistence, it's absolutely represented by an actor. In the replicated entity, it's a little different, but underneath there's still an actor there. So the key point is that each entity is given an actor when it's active. So what I mean by that is that, say we start out with a quiet system, nothing's happening, and then a command comes in for an entity, you say for your bank account. So what happens is that an actor is created for that entity, and then that actor is kind of rehydrated with the state information that was captured in the event log. And say, you know, like in the bank account example, it replays events. Now, there's a save point, and I always use the wrong term, but basically what it is this, I'm sorry, it's a snapshot. There's a snapshot that is a capability that exists where you have something like a bank account that can have a long history. So we want to do every deposit we withdrawal and sum them all up to come back with a bank balance. So when a command first comes in for an entity that doesn't yet exist, it's not in memory, the actor is created, we go and retrieve the point where we've saved the state of the actor, and then we roll through any events that have been recorded since. So it's kind of a quick optimization to get the state back. Then from that point, now that actor is in memory. So any commands that come in after that are going to go straight to that actor. They get routed to that actor, and it's very quick. It's actually kind of a form of a cache if you think about it. And then finally, if no commands come into that actor, after a while, the actor will get, I like to think it gets bored and shuts itself down. Because there's a kind of a timeout mechanism built into these entity actors. So they'll be in memory while they're active, while commands are coming in and events are being stored. And once the activity quiets down, the actor shuts itself down to free up memory. So all kind of built into this whole Akka persistence. And that is with the current Akka persistence as well as the new multi-data Akka persistence.
Okay, thanks for that explanation, Hugh. So there were quite a few questions about Kubernetes. It sounds like we're not going to be able to get to as in depth as some of our audience might like to go today. So I've added a link to our Lightbend Tech Hub with a link to the guide deploying clustered Akka apps on Kubernetes. Now, Hugh, I'm not sure how experienced you are with Kubernetes since it's relatively new. Are you how do you feel about answering a couple questions about how Akka cluster runs with Kubernetes?
I can try. Let's give it a shot.
So one question is basically what does an Akka cluster look like on top of Kubernetes? What's the kind of parallel between Akka like actors, nodes, and pods on Kubernetes pods?
Well, I mean, Kubernetes is new to me, but I play with it some, and the way I kind of look at it is that we can set up Kubernetes so that it runs a process. So in our case, it would be running a JVM, right? And when you configure Kubernetes to run n number of JVMs, the beauty of Kubernetes is that it keeps those pods, those JVMs running. So I think I said the K word back in the early part of the presentation, where I had that scenario where, say, a node went down, and then say I mentioned maybe this cluster is running in Kubernetes, and what Kubernetes will do is it'll restart that process because Kubernetes, say, has been configured to run, say, 3 nodes in this little cluster. And if one of those nodes goes down for whatever reason, Kubernetes is actually watching this. It sees that this happens, and as quickly as possible, it's going to restart that process again and bring it back up. Now, the trick with Akka is that there's a concept of seed nodes, which are known addresses, that when a new node is brought up to join the cluster, the first thing that node needs to do is kind of call home to the cluster. It needs to be injected with at least one or more seed nodes, places where when it comes up and it says, hey, I'm ready, I want to join the cluster, it needs to know who to talk to. So that document that Oliver mentioned talks about how you can deal with this, where you handle the IPs, because the addresses are all, the network addresses are all changing because we're running in a very dynamic environment within Kubernetes. But there is a way to deal with this. So you can form clusters within a Kubernetes environment. It's quite nice then, because now we have an environment where there's the kind of two levels of things going on. There's the actual monitoring that happens in Akka, and there's actual monitoring that happens in Kubernetes. So Kubernetes is kind of watching things at the process level, and Akka is watching things at site within those processes, within the actor system. So it's a nice relationship between the two.
All right, great. Thank you so much for answering that one. I hope that does the trick for our audience out there. There's a question about region handling with Akka. So, for example, with Amazon Web Services, there's regions or collections of availability zones where there's a data center representing that. What is the Akka approach for connecting in this way?
So, I mean, within Amazon, there's availability zones within regions. And this is exactly the kind of playing field that the multi-data center Akka has been designed for. It certainly has been a major consideration here because it's the big player in the cloud. So for us, that's what you're doing. You're defining nodes within a data center, and you identify where those nodes should run. So the idea, kind of in general, is that a data center in Akka is running in some availability zone in some region. But there's really no restriction between where these things run. So you could have one data center running in an availability zone in one region, and another data center, Akka data center, running in another availability zone in another region. You have that option. And this is really the beauty of the multi-data center setup within Akka itself, that looser coupling between these data centers, the kind of the reduced level of monitoring that goes on there. But you can still send messages between actors, between these geographically split up environments. And because like Amazon has West Coast U.S. regions, and it has East Coast, it has regions all over the world. This is the kind of environment that multi-data center was set up for, as well as the fact that this is just configuration as far as Akka is concerned. So you can run all of it, say a multi-data center configuration for Akka within a single availability zone. It's up to you how you want to distribute it. It's just that Akka is more tolerant of outages that occur between data centers than it is with outages that occur within a data center.
Great, thanks for that, Hugh. We have time for just two more questions. Are there any plans to incorporate Akka streams with multi-data center support?
That's a really good question. I do not know. I think that they're working on clustering with streams, but I think we're going to have to go to the Akka team for that one.
Yeah, I was thinking that myself, actually. And the final question that we have time for today is a little bit unrelated to your presentation, but refers to one of the commercial features for Akka, which is called the thread starvation detector. There were two questions asking what that is. Hugh, do you want to take that, or I could even answer that one myself if the audience will allow it?
Go for it, Oliver.
All right, so Akka thread starvation detector. The reason we created this tool is the fact of the matter is that most teams out there do not have the luxury of starting over with a brand new tech stack. So imagine your Oracle database is synchronous and blocking, it's not going anywhere for a while, and yet you've got this beautiful Akka clustered app looking to extend across the data centers of the world. So how do you make sure that your reactive systems do not end up overloading components further down the stream that are not set up to handle asynchronous, non-blocking, distributed communication? This is what Akka thread starvation detector does. It allows you to identify where you're overloading other systems, where you're having thread blocking, and essentially identify where you're going to run into trouble if you keep hammering a legacy technology with millions of actors per minute. And this is a great way. It produces log files and areas of identification where you can track down exactly where things are going wrong and you're bottlenecking your system and having performance degradation. Did I miss anything there, Hugh?
No, it was great. I think you covered it pretty well.
All right. Well, that's I'm glad to hear it. Sometimes a chief storyteller can answer a technical question. Well, folks, thank you so much for joining us today. As I said in the beginning, this is being recorded and will be sent to you sometime next week. So look for that. And thank you all for joining us today. Hugh, thanks for joining us from your hotel room in London. And I hope everyone has a wonderful day.